A farmhouse in Nogent-sur-Seine, France has stood for 440 years without a single structural repair. Its walls regulate humidity automatically. It heats itself in winter. And it was built from a plant that modern construction codes banned for nearly a century. At the end of this video, you will know how to build using it. I am Eddie, and welcome back to Construction Odyssey. Subscribe and hit the bell so you never miss another revelation. In 2015, a team of French researchers arrived at a crumbling farmhouse in the Champagne region with thermal cameras and moisture sensors. The building was called the Maison de la Turque, and local records dated its construction to 1585. When scientists began their analysis, they discovered something that challenged everything they thought they knew about building materials. The walls were made from the woody core of hemp plants mixed with lime and water. After 440 years, those walls showed no signs of structural degradation. The hempcrete continued to harden and strengthen over centuries through a process called carbonation. The lime was slowly absorbing carbon dioxide from the atmosphere and converting back into limestone. This farmhouse was not decaying, it was petrifying into rock. Thermal imaging revealed that interior walls maintained a nearly constant temperature regardless of what was happening outside. Researchers measured humidity levels that stayed between 40% and 60% year-round. That is the exact range that prevents mold growth and respiratory problems. This building was actively regulating its own internal environment like a living organism. This was not an isolated discovery. Civilizations across 3 continents independently figured out that mixing hemp fibers with lime created something extraordinary. In the Ellora caves of India, archaeologists documented hemp fiber reinforcement in lime mortars dating back to the 6th century. 1,200 years later, those mortars remain intact, while concrete patches applied in the 1970s have already cracked and crumbled. In France, you will find Merovingian bridge abutments from the same era with hemp fibers woven throughout the lime matrix. In Japan, a plastering tradition called shikui has incorporated hemp fibers since at least the 1400s. Japanese builders discovered that hemp fibers prevented cracking and added tensile strength to resist earthquakes. Builders in India, France, Japan, and throughout the Mediterranean world converged on the same solution. So, if ancient builders across 3 continents knew this secret, why do you not know it? The answer involves one of America's most powerful industries, and a competitor they needed to destroy. The year was 1937. Legislation called the Marijuana Tax Act imposed registration requirements and transfer taxes on all cannabis varieties, including industrial hemp. To understand why, you need to know 3 names. Andrew Mellon was Secretary of the Treasury and primary investor in DuPont Chemical Company. In 1935, DuPont patented nylon, positioned to replace natural hemp in rope and textiles. But hemp was cheaper, stronger, and farmers already knew how to grow it. William Randolph Hearst owned the largest newspaper empire in America, dependent on paper made from wood pulp. He owned vast timber holdings. In 1916, the USDA predicted hemp would become America's first billion-dollar crop, noting that hemp paper was superior to wood pulp paper. For Hearst, this was an existential threat. Harry Anslinger headed the Federal Bureau of Narcotics and happened to be married to Andrew Mellon's niece. His bureau flooded Hearst newspapers with stories about marijuana madness. The fear was manufactured, and industrial hemp was collateral damage. By the time Popular Mechanics published an article titled New Billion-Dollar Crop in 1938, hemp cultivation was already being strangled. Within a decade, industrial hemp had virtually disappeared from American farms. 80 years of agricultural knowledge vanished in a single generation. In that void, Portland cement took over. The post-war building boom made concrete king. Companies that manufactured cement did not just sell a product. They shaped regulations that determined what could legally be built. They funded research at universities. They placed executives on code-writing committees. Today, the cement industry produces 4.1 billion tons annually, responsible for 8% of all human carbon dioxide emissions. When researchers turned their instruments toward hempcrete, what they found was almost impossible to believe. In 2003, a team at the University of Bath began systematic analysis of hemp-lime composites. Hempcrete insulates roughly 15 times better than concrete. Researchers found that hempcrete combines insulation and thermal mass in a way that no other common building material achieves. A hempcrete wall transmits heat so slowly that warmth never fully penetrates before outdoor temperatures drop. The team calculated that a well-designed hempcrete building could reduce heating energy by up to 90% compared to conventional construction. Professor Sofiane Amzian at the Université de Picardie discovered that hempcrete walls could absorb and release up to 596 kilograms of moisture per cubic meter. The material acts like a massive sponge that automatically regulates humidity without mechanical assistance. Mold cannot grow when humidity stays below 60%. Dust mites struggle to survive. Buildings made from this material are healthier to live in. The most remarkable discovery came from life cycle assessments. Hemp plants grow extraordinarily fast. A single hectare absorbs approximately 15 tons of carbon dioxide in just 4 months. When mixed with lime, the carbon stays locked in the material. As hempcrete cures, the lime absorbs additional carbon dioxide through carbonation. Researchers calculated that hempcrete sequesters approximately 110 kilograms of carbon dioxide per cubic meter. The material stores more carbon than it produces. If just 10% of global construction used hempcrete walls, the building sector would transform from one of the largest carbon emitters into an active carbon sink. Concrete has compressive strength measured in tens of megapascals. Hempcrete measures between 0.4 and 1.2 megapascals. But hempcrete was never designed to be structural. It was designed to be infill. The traditional method uses a timber frame for structural support, with hempcrete packed between posts. When researchers at Cambridge tested this combination, they found hempcrete actually protects timber from moisture damage and temperature fluctuations. The CSTB laboratory in France found that hempcrete achieved a Euroclass B rating for fire safety. When exposed to flame, hempcrete chars on the surface, but the charred layer insulates the interior and slows further damage. The science is overwhelming. That raises an uncomfortable question. Why is hempcrete not everywhere? In cities across America, building inspectors flip through code books that make no mention of hemp lime construction. Architects submit drawings and receive rejection letters citing lack of approved testing. Banks appraise hempcrete homes at lower values. Building codes that govern construction are written by committees that include representatives from material manufacturers. The concrete industry has occupied seats on these committees for decades. A new building material needs testing that can cost hundreds of thousands of dollars. Then it needs a track record of successful installations. But installations cannot happen without code approval. The system is circular. A material used safely for 400 years cannot get approved because it lacks a modern performance record. Architecture programs teach students to design with steel, concrete, glass, and engineered wood. Hempcrete appears in perhaps a single lecture during an elective course. Contractors face the same knowledge gap. Insurance companies have almost no data on hempcrete structures. Every one of these barriers is rational individually, but the cumulative effect is a system that protects itself from change. But something remarkable is happening in places that refuse to wait for permission. In 2023, France certified its 3,000th hempcrete building. In 18 years, France went from a handful of experimental projects to a recognized construction method with full regulatory acceptance. Residents report heating bills 60% lower than comparable conventional homes. The United Kingdom followed a similar path. Today, hempcrete is a recognized material in British building codes. Haverhill contains 42 hempcrete homes occupied since 2001. 23 years later, those homes require virtually no maintenance. The 2018 Farm Bill removed industrial hemp from the controlled substances list. In 2019, Kentucky alone planted 60,000 acres. Building codes are following. Montana approved hempcrete in 2021. Washington State followed in 2022. California has active pilot programs. French contractors report that hempcrete wall systems now cost roughly the same as conventional insulated stud walls when factoring in elimination of separate insulation, vapor barriers, and humidity control systems. In Austin, Texas, a company called Hempitecture has completed multiple projects using domestically sourced materials. In Colorado, the nonprofit Veteran Cannabis Project has partnered with builders to construct hempcrete housing for formerly homeless veterans. The first hempcrete housing development built speculatively sold out before completion. 440 years ago, a farmer in France mixed hemp with lime and built walls that would outlast everything around them. Then for 80 years that chain of transmission was broken, but knowledge wants to be recovered. Today you know there is a building material that insulates 15 times better than concrete, that regulates humidity automatically, that absorbs more carbon than it produces, that gets stronger over centuries instead of weaker. And you know that the reason it disappeared had nothing to do with performance and everything to do with industrial competition. Hempcrete is a biocomposite material made by mixing hemp hurd with a lime-based binder and water. It is not structural and must be used with a timber or steel frame that carries building loads, while hempcrete fills cavities as insulation. The material offers R2 to R2.5 per inch, excellent moisture regulation, natural fire resistance, and carbon sequestration that can make it carbon negative over its life cycle. Hempcrete can change how we build and how we think about carbon. Measure each wall's length, height, and planned thickness, then multiply to find volume in cubic meters. Exterior walls should be 25 to 30 centimeters thick for adequate thermal performance, while interior walls can be 15 to 20 centimeters. Each cubic meter requires approximately 160 kilograms of hemp hurd and 100 kilograms of lime binder, though ratios vary by manufacturer. Add 20% to account for waste, spillage, and learning curve inefficiency. Find construction-grade hemp hurd through the U.S. Hemp Building Association or suppliers like Hempitecture, American Hemp, or Hemp Traders. Request samples and check that pieces are uniformly chopped to 10 to 25 millimeter lengths, clean without excessive dust, and free of musty odors indicating mold. For binder, purchase a formulated hempcrete-specific product rather than generic lime or Portland cement. Tradical hempcrete from France is widely proven, while American lime technology offers domestic alternatives. Store binder in sealed bags in dry conditions, since lime reacts with moisture immediately upon exposure. For mixing, use a drum-style cement mixer of at least 150 liters for larger projects, or a mortar mixing tub with a mixing hoe for smaller ones. Gather 5-gallon buckets, a wheelbarrow, and a garden hose with an adjustable nozzle. For formwork, purchase 3/4-inch plywood to create panels approximately 50 to 60 centimeters tall that span between studs, plus 2x4 or 2x3 lumber for cleats and exterior grade screws for assembly. Make tamping tools by attaching a 15-centimeter square of plywood to a 75 to 100-centimeter handle, plus a narrower tamper for corners. Safety equipment should include N95 respirators, safety glasses, rubber gloves extending past the wrist, and clothing covering all skin. Mixing and safety are both essential. Snap chalk lines on your foundation for bottom plate placement, checking corners are square by measuring diagonals. Install pressure-treated bottom plates with a capillary break between concrete and wood, fastening every 90 centimeters. Mark stud locations at 40 to 60 centimeters on center, cut studs to wall height minus plate thicknesses, and install plumb using toe nailing. Frame openings with king studs, jack studs, headers, and cripples as needed. Install the top plate across all studs. Add diagonal corner bracing or structural plywood sheathing for lateral stability, wrapping exterior sheathing with a breathable weather barrier. Frame carefully and add bracing for lateral strength. Wearing protective equipment, add dry hemp hurd to your mixer and fill to 2/3 capacity, then begin mixing while slowly adding half the batch water. Mix until all material is moistened, then gradually add lime binder and mix 3 to 5 more minutes until every particle is coated with lime paste. Work methodically and let curing, formwork, and finishing follow the schedules recommended by your binder manufacturer. Test by squeezing a handful firmly. It should hold together without crumbling and release only a few drops of water. Adjust with small water additions if too dry, or add more hurd and binder if too wet. Attach form panels to both sides of the wall frame at the bottom plate, secure cleats to studs, and verify a consistent cavity width. Shovel hempcrete into the cavity in 15 to 20 centimeters loose layers, pushing material into corners by hand. Tamp each layer with firm vertical strokes until the surface becomes springy and no longer compresses. Continue adding and tamping layers until you reach the top of the forms, then strike off excess. Move forms along the wall, filling adjacent bays and ensuring good contact at joints. After completing the first lift along all walls, allow it to rest overnight. Wait at least 12 hours and longer in cool weather before removing forms. Test by pressing your thumb against the hempcrete. It should hold its shape with only a shallow impression. Pull forms straight away without twisting, examine for voids or soft spots, and repair defects by pressing fresh hempcrete into problem areas. Reattach forms for the second lift with bottom edges resting on the cured first lift, offsetting vertical joints by at least 20 centimeters. Mist dried surfaces lightly before adding fresh material. Repeat until the walls reach full height. Residential walls typically require 4 to 5 lifts. Pack the final gap at the top plate with slightly drier hempcrete pressed upward. Allow walls to cure at least 4 weeks before applying finishes, maintain good air circulation, and protect from rain. The lime carbonates by absorbing carbon dioxide and progressively hardens over months. Avoid freezing conditions during early curing. After curing, brush surfaces clean and apply breathable lime plaster in 3 coats. First, apply a 6 to 10 mm scratch coat and score it for keying. Next, apply a 6 to 8 mm brown coat and float it for evenness. Finally, apply a 3 to 5 mm finish coat and trowel to the desired texture. Allow each coat to cure for 1 week while misting to prevent rapid drying. Never use cement products, acrylics, or non-breathable finishes that trap moisture. The buildings we construct today will stand for decades or centuries. They will either continue pumping carbon into the atmosphere or start pulling it out. The concrete industry spent 80 years burying hempcrete. If this video changed how you see construction, subscribe to Construction Odyssey with Eddie. Please watch the next video appearing on your screen right now.